Science for a project. And my question was, does a radiant barrier keep an object cool? So a couple weeks back, my father was up here, and I asked him if it was okay to come up. And when I did, I saw a lot of boxes and a couple spiders. But most importantly, I saw all of this. And I asked him, I was like, what's all this aluminum foil doing up on our attic? And he said, first off, it's not aluminum foil. It's a radiant barrier, and a radiant barrier keeps our house cool by blocking the sun heat. And this kind of stuck with me. And a few weeks later, when I had to come up with a science fair idea, and I wondered maybe I could test a radiant barrier. So during my research of radiant barriers and radiant energy, I found out that radiant energy comes down from the sun 92 miles away and hits Earth, and it's also a part of the invisible light spectrum. And everyone actually has felt radiant energy before, either when you're walking out in the sunlight and you feel the sun heating up your body, or if you've ever been by a campfire on a cold night, you can feel the warm, cozy heat on your front side coming from the fire, but your back side is kind of cold with like the rest of the atmosphere. So that is radiant heat hitting your entire front side. Now, in Florida, especially in Florida, hot summers, no one really appreciates radiant energy down here. So, and Florida roofs can actually go up to. Florida roofs are made of tiles, which can heat up to 150 degrees Fahrenheit or up to 180 degrees Fahrenheit. And when the tiles get really hot like this, the radiant energy comes out from them and goes into your house. And then you're just paying for conditioned air when all this radiant energy is coming in, so you're just wasting money at that point. What a radiant barrier does is help you save more money, actually, by when you put it up, when the roof tiles try to do that, the radiant barrier is reflective like a mirror, so it reflects it back out, and so when it reflects it back out, it just goes back into the tile or out into the atmosphere. Now I'm going to be going on to the part where I'm going to be making the entire experiment. So, thank you. I thought about how I was going to design this experiment. I thought about the roof down here in Florida. They're made of tile. So what I'm going to be using are two 18 by 18 ceramic floor tiles, and I'm going to be making them black. Black is because black is a color that absorbs the most energy. Afterwards, I'm going to take the tiles and put them over each other with 4 inches of space between, because there needs to be an air gap. Because if the air gets hot and becomes a conductor, it's going to heat up the backplate and then just be bad. So after that, I'm going to take it outside, and when I'm going to be doing the experiment, the front face will be facing the sun and the back face will be in its shadow. I'm going to be taking the temperature of the front face and the back face over time. Now, what I expect to happen is that the front face will get hot from the sun and then begin to radiate over to the back face, and the back face will become hot too. And then both sides will be hot. Now, after we let it cool down, we are going to start the second part of the experiment. The entire setup will be completely the same, except for the fact that we will be installing a radiant barrier. Now, when I install a radiant barrier, I have to make sure that it does not touch the front face, because if it touches the front face, it will become a conductor and be irrelevant. Now, after I safely secure it between the two faces, I'm going to check the temperature for the front face and the back face over time. Now, after that, I think my hypothesis of what's going to happen is that the front face will get hot and then radiate to the back face like I had done before. But since the radiant barrier is in between, the radiant barrier will reflect that back to the front face. Now, what I think that will happen to the back face is that it will see little or no increase in temperature. and mainly stay the same. Okay, so the following will include the construction of my apparatus, me doing the experiment, and my conclusions. Hi. Okay, so now we're going to be doing the actual building of the experiment. Now, as you can see here, I got 2 pieces of tile. It's made of porcelain, and it's 18 by 18 inch. I'm going to be painting this tile with a black chalkboard paint. But I mainly use chalkboard paint because it is a flat color and it's a dark color, and dark colors absorb a lot of heat. Now, before I can't entirely paint this entire thing black, I first have to get measurements of how much of the space in the corners I need to reserve. This is the space I need to reserve it for. I'm going to be cutting this into 4-inch pieces for all sides, but I gotta make sure that it has its own space so that I don't paint over it. Now I'm going to draw in a line and maybe a little bit over the board, give it a little bit of space, and then, and then measurement. It's about alrighty, completely done. So I'll move that one up a little bit to dry. Alright, so now move on to cutting the wood. Okay, so we let these tiles dry overnight, and now they're completely done. Now I'm going to be flipping this over and painting the other side. I won't be leaving corners like these because I won't be gluing wood to the corners of the tile. All right, so let's get this started. Oh, it's heavy. Oh my gosh. Okay. Okay. Started.
Okay, you could stop and say, all done.
Okay, all done.
Again.
All done. Alright, now I'm going to be cutting all of the pillars. Alright, got all 4 done. Okay, so the tiles have finished drying, but as you can see, there are some scratches on the tile. It was in the process of moving. But after this process, we're going to be touching up and fixing them. Now, to explain a little bit of what I'm going to do, I'm going to take this tile and flip it over, and then take both tiles and flip them over, and then take the wood and put the glue onto the wood and place it on all tiles, and then placing the top tile on top of all the wood. Okay.
It's good. Okay, say you're all done.
Okay, all done. Okay, so I'm currently taking the temperature of the front face, and it is 105.6. So that will be. I would like to note that it's pretty windy out today, and it's pretty cool. So the wind is facing the back, so the temperatures have been kind of decreasing and increasing. The back face is 69.8. We're not sure if this actually might work, but all I know is the front face has been doing pretty well. It's the back face that we're kind of worried about. Like I said, it's decreasing and increasing in temperatures, mostly because of the wind and the cool stuff. So we tried to do the experiment outside, but there were too many variables, such as the clouds blocking the sun, or the winds cooling off the plates. So instead, I decided to bring the experiment back inside, where there will be no variables to mess around with my experiment, and I'm going to be using a heat lamp as my new sun to heat it up. Everything, other than that, everything will be exactly the same. I will still be counting the time every 30 seconds on my timer with my chronometer, and I will still be using the same radiant barrier I will be using for the other one. Okay, so now I'm going to be starting the experiment. I will be running the clock if you can turn the light on, please. We're going to be inserting the independent variable into the experiment, aka the radiant barrier. The radiant barrier can be absolutely anything reflective, and as long as it's reflective, it can reflect back the radiant heat and such. So we're just going to be using household aluminum foil. I've installed the radiant barrier, and if you look closely there, I've made a gap between the front face and the back face because if the radiant barrier touches the front face, it will start conducting and become irrelevant. Now we're going to be doing the entire experiment exactly the same amount of time, 30 seconds, same thermometer, and same book. Everything will be entirely the same. Now we're going to be taking the initial temperature. A second to adjust. Alright, 73. 73. Alright, and the back. 73.4. Oh. Okay. Now, if you could please turn on the sun lamp, please. All right. I initially wanted to run the experiment outside, but the clouds and the winds were making my experiment temperatures fluctuate too much. So instead, I decided to take it back inside and use a sun lamp. I did a total of 5 trials, 3 without the radiant barrier and 2 with the radiant barrier. The results were consistent throughout the trials. The trials I ran without the radiant barrier were went up the front plate went up from room temperature to 230 degrees Fahrenheit, and the back plate went from room temperature to 95 degrees Fahrenheit. There was a difference in the back plate. There was a 20-degree difference from the room temperature to 95. Now, in the middle there was a gap so that there was airflow could be happen when it got hot, so that the air wouldn't become a conductor and heat up the back plate. And I also would like to point out that it was hottest in the center of both plates because the sun lamp was facing the center of the front plate, and so the most heat would be transferred to the back plate in the center. During the trials with the radiant barrier, the front plate heated up to a max of about 250 degrees Fahrenheit, which was actually 20 degrees more than what it had heated up with the version without the radiant barrier. The back plate showed virtually no increase in temperature. In both trials with the radiant barrier, the back plate actually decreased in about 3 degrees Fahrenheit. In conclusion, the trials without a radiant barrier allowed radiant energy to travel to the back plate across the 4-inch air gap. In these trials, the back plate increased in temperature by 20 degrees Fahrenheit. When I installed a radiant barrier in the front of the back plate with a proper air gap, the temperature did not increase, proving that the radiant barrier did shield the back plate and kept it cool. Interestingly, when the radiant barrier was installed, the front plate reached temperatures 20 degrees Fahrenheit higher than when no radiant barrier was present. The evidence that the radiant energy was being reflected back to the front plate. Another interesting occurrence was that in the trials with the radiant barrier, the back plate actually decreased in temperature, about 3 degrees Fahrenheit. I believe this was due to the chimney effect and was happening between the plates. The hotter the front plate got, the more air was being heated and rising. It wasn't happening. all done with the experiment. What am I supposed to do with this perfectly good aluminum foil? Oh, I've got the perfect idea. I love radium